Hello friends, welcome to UGC EPG Pathshala. I am Professor Masood Hassan Siddiqui from Department of Geography, Jamia Millia Islamia. Today we will be discussing about the map projections. Map projections are systematic transformations that allow the orderly representation of the Earth's spherical reticule on a flat map. Mathematically speaking, map projections are transformation of geographic coordinates, that is latitude and longitudes, into a Cartesian coordinates, xy coordinates, space of the map. A map projection is the manner in which the spherical surface of the Earth is represented on a two-dimensional surface. The term projection comes from the notion of placing a light source inside a transparent globe and projecting shadows of the meridians and parallels onto a sheet of paper placed tangent to the globe. It can be defined as a systematic arrangement of intersecting lines on a plane that represent and have one-to-one correspondence with the meridians and parallels on the datum surface. Each map projection has certain strengths and weaknesses in terms of accuracy of shape, area, distance, and direction. It is not possible for any of the projections to retain more than one of these characteristics over a large part of the Earth. It is important to recognize that because of the curvature of the Earth, all map projections distort distances and direction relationship. The effect of curvature on the distance and directions can be safely ignored for a small area, but for a larger area, distortion cannot be avoided. The classification should follow a standard pattern so that any regular non-conventional can be described by a set of criteria, and conversely a set of criteria will define a regular projection. The classification scheme is as follows. Classification on the basis of plane of projections. These are the first order projections. It includes planar, that is azimuthal, planar or zenithal projections are accomplished by drawing lines from given perspective point through the globe on a tangent plane. A tangent plane intersects the global surface at any one point and is perpendicular to a line passing through the center of the sphere. Thus, these projections are symmetrical around a chosen center or central meridian. Choice of projection centers determines the aspect or orientation of the projection surface. Planar projections may be centered on the poles, what we call as the polar aspect, at a point on the equator or at any other orientation, that is oblique aspect. The figure 1 depicts the zenithal projections. The origin of the projection lines, that is the perspective points, may also assume various positions. For example, it may be the center of the Earth, which is mnemonic, an infinite distance away. Orthomorphic are on the Earth's surface opposite the projection plane, that is stereographic. Meridians are projected as straight lines radiating from the center, that is pole, and is placed at true angles. The parallels are complete circles. The important features of this category of projections are: only a part of the Earth's surface is visible, distortions will occur at the four corners, distance for the most part is preserved. The conical projections are accomplished by intersecting or touching a cone with a global surface and mathematically projecting lines on this developable surface. A tangent cone intersects the global surface to form a circle. On this line of intersection, termed as the standard parallel, the map will be relatively error-free and poses equidistance. Cones may also be secant and intersect the global surface, forming two circles which will possess equidistance. The word secant in this instance is only conceptual, not geometrically accurate. As with planar projections, the conical aspects may be polar, equatorial, or oblique. It has been assumed that the center, the pole, and the vertex of the cone are in a straight line. The cone touches the globe at 2 points. These points are neither the pole nor the equator. It means the points are lying in between the pole and the equator. The parallels are arcs of circles drawn using the vertex as the center, and the meridians are straight lines radiating from the vertex at equal angles. The figure 2 shows the positions of the conical projections. The important features of the conical projections are: scale for the most part is preserved, distance is distorted towards the bottom, area is distorted. The third one is the cylindrical projection system. Cylindrical projections are obtained by intersecting or touching a cylinder with the global surface. The surface is mathematically projected on the cylinder, which is then cut and unrolled. A tangent cylinder will intersect the global surface on only one line to form a circle with a tangent cone. This central line of projection is generally the equator and will possess equidistance. If the cylinder is rotated 90 degrees from the vertical, the long axis becomes horizontal, the aspect becomes transverse, and the central line of the projection becomes a chosen standard meridian. The figure 3 shows the normal cylindrical projection systems. Because of tangency, the scale is true at or near the cylindrical line, central line. The meridians are parallels and equispaced, vertical straight lines intersecting the equator at right angles and divide the globe into 360 parts. The parallels are horizontal lines drawn from east to west. All the parallels are equal to the length of equator. The amount of distortion increases towards the pole. The important features of cylindrical projections are: number one, the position of the countries near the equator is true to a large extent. Distortion is maximum at pole. Area for most of the part is preserved. Second order projections are tangent, base, secant, polysuperficial, which includes a series of successive projection surfaces. These three approaches are applied to minimize the area of distortion by intersecting the globe instead of touching it. A flat plane will intersect the globe along a circular line, whereas the cone or cylinder along two circular lines. Thus, by intersecting the generating globe, the extent of distortion-free area is increased from a point to a line in case of a flat plane, and from line to two lines for cone and cylinder, meaning thereby there will be two standard parallels instead of one. The distortion-free area may further be increased if more than one identical shape surface are made tangent to the globe. It will result polyconic for successive cones, or polycylindrical for successive cylinder, or polyhedric for successive plane projections. On the basis of the nature of contact to the generating globe, the projections may be called as tangent, secant, and polysuperficial. The third order projections are normal projections, transverse projections, and oblique projections. Alignment of generating projection surfaces with respect to the datum surface results to the three types of projections. If the axis of symmetry of the plane of projections is coincident with the rotational axis of the generating globe, it is said to be normal. The normal, transverse, oblique, all these are shown in figure 4. The cylindrical projections, if however the axis of symmetry of the projection surface is at right angles to that of the generating globe, a transverse case is attained. That is, the axis of the cylinder is at 90 degree to the polar axis. If the axis of symmetry of the projection surface is in between the two intersects at an acute angle, we get an oblique case. Projections are also classified on the basis of the methods of projections. These are perspective projections. The projections in which it has been imagined that a series of rays are emerging from a source of light and they pass through a transparent globe to cast the shadow of the parallels and meridians on the projection surface. The surface may be cone, cylinder, or plane. All of these surfaces are developable and can be unfolded without distortion. These are also known as geometric projections. Changing the position of the light, the source alters the pattern of parallels and meridians on the map, resulting in maps that have different geometric properties. The underlying figure shows the perspective projection systems. The non-perspective projection systems are the modified perspective projections for achieving certain desired properties such as true areas, shape, directions, and bearing. If the mutually intersecting lines are drawn on the projection surfaces without any reference to the surface of light, that is, no rays are plane are involved but are achieved by a mathematical operations, such projections are called as non-perspective projections. The classification of map projections based on the quality gives three mutually exclusive varieties representing the intrinsic geometrical properties. These are homolographic, that is the equal area, orthomorphic, that is conformity or true shape, azimuthal, that is true bearing, equidistant. Equivalency indicates that the areas of the figures are retained on the projection surface as compared to the datum surface. This, however, takes place at the cost of the shapes and angles getting distorted. This is used best for spatial distortion and relative sizes of the spatial features. For example, political units, population distributions, land use, and natural resources, etc. Albert's conical, Lambert's conform, cylindrical, and sinusoidals are the typical projections of this category. Typically, reference lines such as the equator or the meridians are chosen to have equidistance and are termed standard parallels or the standard meridians. Conformality means retention of the shape or forms, also retentions of the angles. This property is limited to close points and not to the areas of significant dimensions. The angle of intersections of the meridians and the parallels is as it is on the globe, that is, the meridians intersect parallels at right angles, just at globe. These are also called the conformal or orthomorphic projections. These are widely used for topographic mapping and navigation purposes. Mercators and its various variants are typical example. The true direction projections are characterized by directional lines between 2 points which crosses reference lines, for example, meridians at constant angle or azimuth. These are termed rhumb lines, and this property makes it comparatively easy to chart a navigational course. However, on a spherical surface, the shortest surface distance between 2 points is a great circle along which azimuths constantly change. Thus, a more desirable property may be where certain great circles are represented by straight lines. This characteristic is most important in aviation. All meridians are great circles, but the only parallel that is great circle is the equator. This particular property can be retained with some other qualities of the projections. For example, conformal projections retain the true direction. Typical example of this type are the variants of azimuthal and Mercator's projections. The equidistance mean there is correct representation of distance between 2 points on the projection surface as compared to the distance on the datum surface. This property is limited to certain specified sets of points and is not a general property between the points on the two surfaces, for example, along central meridian in case of cylindrical projections and along standard parallels in case of conical projections. Such projections are generally used in atlas maps. Typical examples are azimuthal equidistant and equidistant conic projections. Although a great number of projections have been devised, the majority of them are geometric or mathematical variants of basic direct geometric projection families described above. Choice of the projection system to be used will be depend upon the true property or combinations of the properties desired for effective cartographic analysis. The important map projections are universal transverse Mercator's projection, that is known as the UTM, and that is to be discussed over here. The UTM is a modified version of Mercator's projection. It is probably the most famous projection of all time and the best map projection for navigators because of its unique quality that an earthbound traveler following a line of constant compass directions can chart the course on the Mercator's projection with a straight line. This quality was not accidental. Gradress, the developer used a logarithmic displacement of the parallels of latitude to obtain this effect as a service to navigators. Because of the fact that the standard Mercator's map is tangent to the Earth at the equator, it represents size and scale only in lower latitude and grossly overestimates them near the poles. Consider that the North Pole is actually a point but in a cylindrical projection, but it is exploded to a line. The UTM is a conformal projection and preserves the shape of the features such as coastlines and river sands largely used in GIS. Lambert projection is another important projection which is largely used for mapping all over the world. Lambert J.H. 1772 modified this equatorial Mercator projection by changing the aspect of projection to transverse with a view to minimize the distortion in a narrow strip running from pole to pole. Later, Gauss in 1822 and Kerger in 1912 and 1919 modified and adjusted for polar flattening. Thus, it is also known as Gauss-Kerger projection. It is a cylindrical projection with the axis of projections lying perpendicular to the axis of symmetry of datum surface, that is, the ellipsoid. That is, instead of using the standard parallel, as in the case of Mercator's projection, the transverse Mercator's projection uses the standard meridian in order to minimize the distortion that occur in the transverse projection. Further modifications were made. The modified transverse Mercator's projection is called as universal transverse Mercator's projection. It loses the properties of a straight meridian and parallels to the standard Mercator's projection. Transverse Mercator also loses the straight line, but it is conformal projection. Scale is true along the central meridian or along two straight lines equidistant and parallel to the central meridian. It is repeatedly applied by using multiple cylinders that touch the globe at 6-degree interval. The cylinder is made to intersect the globe at two standard meridians that are 180 kilometers east and west of the central meridian. The UTM defines two-dimensional horizontal positions, consist of 60 zones of 6 degrees of longitudes in width, each extending 3 degrees east and 3 degrees west of the central meridian, extending between 80 degrees south to 84 degrees north latitude. An additional 1.5 degree that is equivalent to 40 kilometers on each side provided for overlap into the adjacent zone. The first zone starts at 180 degree west to 174 degree west with 177 degree west as central meridian. The final zone 60 degree, that is the zone 60, starts at 174 degree east and extends east to the international date line. The figure 6 shows the transverse Mercator's projection, and the figure 7 is showing the overlap in the UTM. Table 1 shows the UTM zones with their numbers and central meridians, whereas the figure 8 shows the transverse Mercator's projection system. The central meridian is a great circle and is the only line of latitude or longitude represented by a straight line in the map projection. Each UTM zone is divided into horizontal bands of 8 degree longitude. These bands are identified by letters south to north, starting at 80 degrees south with letter C and ending with letter X. Letter I and O are omitted, whereas letters A, B, Y and Z are reserved for the universal polar stereographic coordinate systems. This projection system is largely used for large mapping projects like the National Map Series produced by the US Geological Survey and the Ordnance Survey of Britain and France. The UTM coordinate systems is based on the transverse Mercator's projections. The students of geography know that equatorial Mercator's projection distorts areas so much towards the pole that Greenland appears about 7 times bigger than India. However, the distortion is minimum laterally along the equator. In the geometrical sense, the transverse cylinder is tangent along the cylindrical central meridian of each zone. A scale factor of 0.996 is applied along the central meridian of each zone. The scale factor is simply the ratio between the actual map scale at a particular location to the nominal map scale. The actual map scale is always the ratio of the map distance to the ground distance. This results in the transverse cylinder becoming a secant to the datum, and the scale distortion is more favorably distributed over the zone. The choice of the scale factors of 0.996 was made so as to limit the scale error to 1:2500 within the zone. There are special UTM zones between 0 and 36 degree latitude above 72 degree latitude, and a special zone 32 between 56 and 64 degree north of latitude. Figure 9 shows the Mercator's grid system, northern and southern hemisphere. For areas beyond the 80 degrees south and 84 degrees north, the universal polar stereographic projection is used. This is an azimuthal projection obtained by projecting from the opposite poles. All of either the northern or southern hemisphere can be shown as a map, but not both. This projection produces a circular map with one of the poles at the center. Polar stereographic stretches areas towards the periphery and scale increases for areas further from the central pole. Meridians are straight and radiating parallels are concentric circles. Even though scales and area are not constant, this projection, like all stereographic projections, possesses the property of conformality. A grid system is superimposed upon the polar stereographic projection with the provision of half-degree overlap. The vertical grid lines are parallel to the meridians 0 degrees and 180 degrees, whereas the horizontal grid lines are parallel to the meridians 90 degree west and 90 degree east longitudes. Though the origin of the grid is the pole, but an arbitrary false easting and false northing of 2 lakh meters is assigned. The scale factor is set arbitrarily as 0.994 at pole. The scale is true to the grid at 810, whereas at 800 the limit of UPS systems. The scale is large by factor of 1.0016. The UTM coordinate system has been widely used for large scale topographic mapping all over the world and even for mapping of planet Mars. Another projection system is the Lambert's conformal conic projection. The Lambert conformal projection is one in which all the angles are preserved and scale factor is constant in any direction. The Lambert's conformal conic projection was developed by John Henrik in 1772 to provide a minimum of angular and scalar distortion. It is conformal map projection of so-called conical type on which all geographic meridians are represented by straight lines that meet in a common point outside the limits of the map, and the geographic parallels are represented by a series of arcs of circles having this common point for a center. Meridians and parallels intersect at right angles, and angles on the earth are correctly represented on the projection. This projection may have one standard parallel along which the scale is held exact, or there may be 2 such standard parallels, both maintaining exact scale. At any point on the map, the scale is the same in every direction. It changes along the meridians and is constant along each parallel. Where there are 2 standard parallels, the scale between those parallels is too small. Beyond them, it is too large. The straight lines plotted are approximately great circles. These are used for VFR, this is called as the visual flight rules, analytical charts, etc. The figure 10 shows the Lambert's conformal conic projection system. Projection systems with one standard parallel. It is a secant conical projection. The parallel are chosen to minimize errors over the area of interest. On the standard parallels, arcs of latitudes are represented in their true lengths or to an exact scale. The scale is too small between the standard parallels and too large beyond them. This projection is best suited for mid-latitude areas, especially with east-west dimensions. The major property of this projection is its conformality. At all coordinates, meridians and parallels cross at right angle. The correct angle produces correct shape. Also, great circles are approximately straight. This projection is useful for landmark flying. Lambert's conformal conic is the straight plane coordinate system projection for states having an east-west expanse. Since 1962, Lambert's conformal conic has been used for the international map of the world between 84 degrees north and 80 degrees south. It possesses true shape of small areas, whereas Albert's possesses equal area. Another projection system of equal importance is the Polyconic Projection system. This was developed in 1820 by Ferdinand Hassler, specifically for mapping the eastern coasts of US. Polyconic projections are made up of an infinite number of conic projections tangent to an infinite number of parallels. These conic projections are placed in relation to a central meridian. Polyconic projections comprise properties such as equal area and conformity. Although the central meridian is held true to the scale, the figure 1 depicts the conical projection system. All parallels are arc of circles but not concentric. All meridians except the central meridians are concave towards the central meridian. Parallels crosses the central meridian at equal intervals but move farther apart at east and west peripheries. The significant properties of conical projections are all the parallels are standard parallels and the scale is correct along the parallels and the central meridian. All meridians except the central meridians are concave towards the central meridian. Intersection of parallels and meridians are rectangular. Scale is distorted away from the central meridian. Polyconic projection compromises properties such as equal area and conformity, suitable for the areas with large latitudinal and small longitudinal extent. The Survey of India uses polyconic projection for its topographic map series on 1:2000, 1:250,000, 1:50,000 and 1:25,000 series. The USGS also uses it for the topographic map series on 1:24,000. Since there is a large list of the map projection systems and all projections are not suitable for all purposes, therefore the following table number 2 depicts the important map projection systems useful for different purposes and for different reasons. With this, we end the lectures on the map projection systems. Thank you very much for your patience listening. Thank you.